Hello everyone. This is Aditya from HackSlash Machine Learning team, and I'll be taking this third lecture in the series of study jams conducted by HackSlash on the topic of linear regression. Let's get into it. In the previous two sections, you have studied about machine learning and basis of Python. Right now we will deep dive into linear regression. So basically, linear regression, there are two words, linear and regression. What does it exactly mean? So if we go by the grammatical, the English definition, linear basically something which is a straight line, and regression means, in terms of machine learning, prediction of a numerical value here. So basically, we will be given some set of data which will point to another data, and we have to predict if another set of data is given, what to what data will it predict with respect to the first mapping which was given to us. So at this place, we have a dependent variable and an independent variable, and we plot the points. So at this point, the independent variable, the data will be pointing to this point in the dependent variable in the two axes. So let's assume we have some random points and we plot it. We make a straight line. I'll be telling you what this straight line means and how to, uh, and how to go around about it. Be with me during the lecture. So what we are trying to understand is, as independent variables are changing, how does dependent variable change? So basically, how are they related to each other? So this line which you are seeing is known as the regression line. And so basically, there are two types of line which you can draw: a positive relation, a negative relation, if dependent and independent variable increase in the opposite direction. And so this is all basics. So if we plot observations and find a straight line which fits all this different point, I'll tell you what this means. And this line is drawn upon least squares method, minimum, the difference between the estimated and real value. So basically, what does mean is, we draw a straight line and we calculate the distance, the straight distance, not the perpendicular distance, which you calculate like the Euclidean distance. This is the Euclidean distance. We do not calculate this. We calculate a straight distance. And let's say this is an error. So the estimation and the error. So if we calculate this distance from all the dots like this, we can get like error. So the errors can be E1, E2, E3, something. So the mean squared error is the square of that error. Let's say this is at uh, point K1 and this is point K2. So K1 minus K2 squared. So that will be even squared. So like that, for all the points in the data set, we do it and we get it as 1 upon n sigma summation of all the squares of error. So this is mean squared error. And what we do is try to minimize that error which we get. So we minimize it there is a method for doing that, which is simple gradient descent algorithm, which I'll be telling you. And there is another thing, Adam optimizer. So Adam optimizer is a very advanced thing. It is relatively new, related as compared to simple gradient descent algorithm. So we will be going it, and this mean squared error is can be also called as a loss function. So these two terms are exactly the same. So the loss function is all basically, mean squared error is the uh, the equation which we wrote here, but in at this place we took loss function in terms of mean squared error. If we wanted, we could also take it as normal mean, like 1 upon n, then sigma EI. So what problem, actually we could take it, but what problem arises at this place is, as you can see, there are some dots above the axis and some dots below the axis. So there may be a condition that all of them sums up to zero, because this will be positive error 1, positive error 2, negative of error 3, negative of error 4. So assume in a case that they all equals to zero. So you cannot move the line according to the algorithm, because the algorithm wants the E minimum to be zero. And since it is zero, I mean, I'm saying like there can be more than two places of the axis where the sigma E, the sigma error should be, could have been zero. So it is really hard to estimate that which one of them is a better approximation. So we use a loss function which squares the means, which squares the error and calculates the average. So basically, this is a, what do you call that? Loss function calculated in terms of mean squared error. So this was all about it. Yeah. So algorithm. What gradient descent does is it. Let me go through this analysis. Yeah. So this is squared gradient descent. This is squared mean error. So basically, let's say your error bar is at this place, and we can move downward using a loss function. What is a loss function? I'll tell you in a few moments. So basically, this will move down, and at this place, the loss will be minimum. So what we do is using these two algorithms, simple gradient descent and random optimizer, we try to minimize the loss. So at this place, there is a loss, and this is the learning rate of the model. So basically, the loss function, as I said, this is a mean squared error, but we can also take it as an absolute value if we have to take it as positive. So that will be 1 upon n, then mod of then sigma mod of E of I. But the thing is, this has a lot of problems, because at first the learning rate in the way it will decrease is very linear, and at this place there is a this point is not differentiable. So basically, this is a point. There is no curve at this place. So what can happen is this thing can directly shift here, and it can never reach this place, no matter how small no matter how small your learning rate is. It may happen. I'm not saying that it is exactly the case that it will never reach it, but it may happen. And there are many hidden trials which showed that the squared gradient descent algorithm, I mean the mean squared error using learning rate is a better choice than absolute value or normal value. So if we do a 3D plot, this is how your linear regression algorithm works. This was for a two-dimensional, this is for a three-dimensional. So what we can also do is we can compress the image from one axis such that it becomes a two-dimensional plot. A two-dimensional plot for two-value linear regression. I'll be showing you in the next slides that how this thing happen, and the more values to consider, more dimension it gets into. This is very obvious, because in one axis you will plot one stuff, and another axis you will plot another stuff, and you will leave at least one axis to for the prediction, like what you have to predict. And since only three dimensions are perceived by the human mind, so what to do? So basically, matrices helps in this stuff. We make different matrices, and we put the values in there, and we calculate it accordingly. So basically, you just Google it out that how matrices helps us in calculating stuffs when the dimensions gets out of bound. So how the simple gradient descent algorithm works. So okay, so how does a simple gradient descent algorithm works? So basically, we have a loss function. We update that by multiplying it by a learning rate alpha, and we differentiate it. So basically, at this place, this is all mathematics. You don't have to go deep into it, but this is what happens at this place. We have the loss of the model, and this is not looking good. Okay. So on this side, we have the loss of the model, and this side, we have the amount of iterations. So after some amount of iterations, the learning rate, this is the learning rate, the arrow size. So if this alpha is very big, you can see that the learning rate would be very big. So this can go like this, then this can go like this. But since it crossed the minimum value, it it will go here, then it will come down. So this is very absurd amount of thing. It will take a lot of hits, and maybe there exists a case that it does not reach at this point, the minimum most point. So if we make it small, you can see that the smaller this arrow is, the better probability is that after a certain amount of iterations, this will reach the very bottom of this loss curve. So this was all about theory, and now we will move to code, that how can we write this and run this basically. Yeah. So this I'm running this on Kaggle because I hosted the code on Kaggle, so it's easy for me to run here. So until the CPU starts, let's get here and where the stuff was. Yeah, Atom Optimizer. So basically what I was saying, the simple gradient descent algorithm works on a very simple trick, which is the loss. The decreasing of loss by going down the slope. But did you ever consider that, let's say, what we will do if we have an arrow like this, then the loss gets down at a very fast rate. So it will make it small. The arrow will be a little bit smaller automatically. And so since the bottommost point is not reached, it will become big. Then since it is small, then since it has reached it, so it will make it very small, and this will be smaller, then come back, then it will be smaller. So in this process, in around 5 steps, we get to the bottommost point. So basically, as time progresses, people come up with new optimization techniques, thinking out of the box and doing something very great into this field. So I guess, yeah, so the CPU is on and we will run it. So at first, we will define two numbers, not two numbers, basically list two arrays containing numbers. So I did that previously. So I will go through the code. So what is x is equal to np dot array 1 2 3 4 10, and y is equal to np dot array 3 4 6 8 something something. So np is your numpy array. So we will just import it numpy as np. I hope you are clear about what this does. Import is a function calling the numpy from your previously saved uh, from the NumPy library, I mean, which is previously installed in your uh, local machine, or if you're running on Collab, Collab also has a virtual machine running there. So we were importing NumPy as NP because, I mean, it's easy to write NP instead of NumPy all the time, and we run it. So how does X look like if we just print it out? So X is an array, 1, 2, 3, 4. So if we print, let's say X of 0, it will say 1. For I in range, length of X, let's say print do not have to go into the details. What I did is I did print everything. So x of 0 is 1, x of 1 is 2, x of 2 is 3, x of 3 is 4. So we have a list of x and y having these. So since x and y are of the same shape, as you can do, if length of x equal length of y, then print thing. So both have the same number of elements in them. We can just use this loop to print y simultaneously. Y of I. So we have x of 0 as 1, y of 0 as 3. So basically this is 3 times, this is 3 times, this is plus 1, this is plus 4, this is the same, this is twice. So we have two values to list containing some random value. So we plot it. So how do we plot it? We plot it using matplotlib. No module found out matplotlib dot pyplot. Matplotlib dot pyplot. Maybe it's some spelling error or something. Okay, so we did plot it. We imported the matplotlib as plt. So if we say plt.figure, the figure size, it just changes the figure size. Plt.scatter. So scatter is basically point. It will plot as point. I will tell you how this stuff happens. So x comma y. So plot all x and y. Then plot the title, which is at this place. Plot the x label. Plot the y label, show the legend, show the grid, and plt.show simply just print it out on the screen. So this is the plot. If we, let's say, plt.plot, this is very absurd amount of plotting here. So if we plot as plt.stem, stem got an argument color. Okay, so remove this argument marker. Okay. Okay, so this is the plt.stem, but this is very useless because what we are doing is linear regression. So for this, we have to visualize the data set in a neat way as compared to uh, stupid visualization. So this is your plot. And now we will go into the gradient descent algorithm. As I have said, how the gradient descent algorithm works, I have that stuff in code, and I'll just plot it and show you that how can you move this line. So this line at this place will move something like this, and it will go and stop at a place where the error, this thing, the error rate, the mean squared error is the least. I mean, it is near to the least. So it depends upon the number of iterations and the amount of learning rate. The learning rate is basically this stuff, that how big this arrow would be. So is given to the code such that this line oscillates and give you really good results. So if we run this define linear regression, this runs, and as you can see, this line. So what we did was we did that for 100 times. Okay, so this stuff moved for 100 times, and for each time it updated its mean squared error value and tried to make it small. So what I did is we defined a linear regression. So this is basically for the gradient descent algorithm. So we defined a function named as linear regression, which takes two parameter x and y, learning rate, and the number of epoch. The number of epoch is how many times the model will run. And we defined m as 1, b as 1. M is your typical slope, b is your typical the point on the y-axis where it will cut. Okay, yeah, good. So n is equal to length dot x. So basically this is normal as I told you about. Step rate and MSE value, I'll tell you what it means. So MSE is mean squared error values, that at each epoch, at each iteration, it will store it in that array. This is how you define arrays in Python. So we plot it, and this is basically a learning rate algorithm in code, the gradient descent algorithm. So why prediction? So as I told you, regression is a type of problem where we predict a numerical value in general. After everything is done, I'll teach you how you can use regression to predict to for a classification model. It does not work that good, but it is relatively okay if you want to use a regression for a classification problem. So basically, this is what you call as a gradient descent algorithm. We defined a function, what we usually have, because since we have two values, the y will take two parameters. The function will take two parameters, the predicting value and the independent value. So dm is equal to minus 2 upon n into something something. So this is basically exactly this thing, the mean squared error, and db is equal to this. db is equal to minus 2 by n sum of y minus y prediction. Good to go. So m is equal to m minus learning rate into dm, b is equal to b minus learning rate into dm. Then what we did is the MAC, the mean squared value, we calculated like what I said, np dot mean will give you the mean of every stuff which is inside it. So y minus y prediction into 2. So this 2 is the power, and dot append will add everything into the what do you call that, into the array, into this list. So this is how you do it. And for all epoch, for every epoch, modulo 10, which means after every 10 epoch, we have to plot the figure into this linear regression stuff. And that's it. So if we print it, this is how it works. The mean squared error after 10 epoch is 4.28. So basically, this is not a percentage thing. This is relative, relative to the maximum error which can occur. So at this place, you can see the maximum error is 4.8. So if you have to calculate that how much change you could make, it will be 4.2835 minus 4.8 upon 4.8, something like that. So as I told you, the more the linear rate, the stupid your model will behave. So let's say the linear rate is, the learning rate is 10. So the moment the learning rate is 10, you can see that mean squared error is 21, 2,15,270. And it increases up to 4 point something into 10 to the power 51. So basically, this is a very huge value as compared to 4.28 or something what we were having. So in general, learning rate should be 0.001, and this will give us 4.52. So if we make it as 0.23, it will be 4.28. So let's say 0.20, it will be 4.29. So basically, you have to just do hit and trial and see that which learning rate gives you the better approximation of your thing. So we will go into Atom Optimizer. Atom Optimizer is a bit difficult. So I'll give you the basic thing. Atom Optimizer takes something something as its input. So the learning rate, I told you what it is. Epoch, I told you what it is. Beta 1 and beta 2 are the shifters. They shift the learning rate by some value which betters the coming which betters the loss, which decreases the loss in a more efficient manner. And epsilon is just a number to epsilon is used such that it epsilon just prevents division by zero. So basically, there may exist a case where you divide some function by zero. So epsilon just stops that from happening. As this is very close to zero, the calculation will be nearly approximate and as compared to theory, and it will be good. So as you can see, the moment we run this Adam optimizer, so using Adam optimizer, the linear regression stuff gives us a value of 4.37. So uh, let's say 0.01. It is 4.72. It is a little bit big. So let's say 0 to, so this is 4.44, 08. This is 4.10. So basically what we did, we performed better, a little bit better than the gradient descent method using the Adam optimizer method. So Adam optimizer method and gradient, and since this code is only for two values, like we give x and predict y, it is pretty easy for the model to predict 4.10940 something. But after the final, the thing is, after changing this learning rate, it is possible to get a value of 4.07 something. But in theory, for very big, where very you deal with very, very big numbers or stuffs like that, it is very hard for the model to get a lower loss for using your gradient descent algorithm. So in general, I mean, not in general, it is generally advised to use Adam optimizer. So moving on to some heavy thing. Heavy thing is basically your just give me a moment. Device dot coda trigger model. Okay, so until then, I do not think I have anything else to tell you related to this. So let's wait until this happens. Okay, so it is done. We have our model on the CPU, on the graphics processing unit. So in this case, we generated a new data set. So what I am doing here is using linear regression uh, in terms of neural networks. So how does this work? So what we are doing is, as you can see, if I go to neural net architecture, what neural nets are, they are densely connected uh, s- among themselves, and data is processed between them. But if we use it for linear regression, it will be a straight line. So something like this. So this is basically linear regression architecture in neural network, using neural networks, where each input is connected to the output, only one output without any hidden layer in between. So let's move on to it. So what we did here was we created a data set with three variables and one output, and we generated 10,000 random points, and this is the function here which creates it. So basically that is 2 times x1 minus 3.4 times x2 minus 1.2 times x3 plus 4.2. So I'll tell you this. So basically, what we did was we created a matrix of three values, and we took the first value, the second value, the third value from that, and then we processed it 10,000 times. So we had a data set. So we generated a matrix, we generated a noise because this already is linear, as you can see. So we have to generate a noise for the model to do something and to decrease the accuracy. So if we print the values, we generated three independent values and pointed that to a dependent value, which is y, after adding noise. Uh, so the y1 is the noise and the x is the stuff. So if we plot those stuffs, this is how it would look. We have three values corresponding to the blue, orange, and the green one. And what it does here is it points to a value in the y-axis. So this is a four-dimensional figure. Compressed it. We just compressed it such that it became a one-dimensional figure. So a two-dimensional figure. So basically, we import data set and data loader from PyTorch. PyTorch is a module used for machine learning, and it gives a deep understanding about stuff. So we loaded the data set, the X and the Y, and we process each of them in a batch of four. So this stuff you will get to learn when you do neural networks, and I'll go through it after some time. So if we plot it, what we get is we have data, the x1, x2, x3, and what we have is the corresponding value. Okay, so this is all what is present at this place. So how many data points we have? We have 2500 data points because we processed them in a batch of four. And since it was in a batch of four, the data points would be 10,000 by 4 because we have initially 10,000 linear points, as you can see at this place. The num examples are 10,000. So moving down the line, we have our we defined a linear regression class, and we imported the stuffs inside it from the nn module. So nn module is basically a neural net architecture architecture defining class in PyTorch. So we included that into this linear regression class, and super basically what it does is whatever is called into the linear regression class from another class, this super method defines that for all the functions inside this class. So basically this is some high level theory of Python, not high level but intermediate level theory of Python. So we defined a layer which will input three stuff and output one stuff. So this is a very pretty good to go, as this shows it takes three stuffs and output one stuff. So this is what it is. And if so we will be installing Torch Viz, which will help us in visualizing that how this model looks, how this architecture looks. So let's do that. Okay, so this is how it looks like. It will take 10,000 values, and it will, no, it does not look like that. This did some problem here at this place. Just give me a moment. I guess there is some problem with this, so uh, just leave it for now. What in general it looks like this. We will give three input, and depending upon a weight and a bias, So weight and biases, so this thing at this place, it will become like, just a moment, if I can copy this image here. Okay, I can, yeah, good. So at this place, what we can do is, I mean, how it will process this further is, this will go into x1 into b plus w1, x2 into b2 plus w2, and at this place we will just sum everything whatever is at present, and I will give it into the y1 place. So as you can see that this looks like this, where where the x1 is multiplied by some value, x2 is multiplied by some value, x3 is multiplied by some value, and we have a constant. And what we have to do in the optimization, or you call the loss function, is to predict b1, b2, w1, w2, w3. So basically model making a neural network architecture is exactly like this. We have to predict, we have to find what values of weights, this is weight and this is bias, what value of weight and bias should be given to the model, such that for a particular kind of stuff it will predict, or it will fit the stuff. Fit is a better word for that. So that's it. So what we do is mean squared loss. We will define the loss function as that. We will import the optimizer from torch.optim. We use the optimizer head as SGD, which is a stochastic gradient descent. What I told you in this place here. I will also tell you how it works using the Adam optimizer, but the this is simple gradient descent, or the stochastic gradient descent works exactly the same way, but with a little bit difference is that there is a batch processing size going in the stochastic gradient descent, whereas in simple gradient descent, that batch stuff is not there. That's it. So moving on, what we have is, this is basically the loss function we defined above. So if we run this, what we get is, the model is updating the weights and bias at this place, the B1, B2, B3, W1, W2, W3, to and testing it also to see that is to see that if I am getting this value or not, to minus 3.4, minus 1.2, and 4.2. So, and since we added a noise, where it is, since we added a noise value here, it is obvious that the loss cannot be zero, can never be zero. So we calculated the loss for 10 epoch, and the loss is very, very less. So this is pretty good. As you can see, for 10 values, uh, where it is, yeah, for 10 values, uh, when we use the linear regression, the machine learning part, where you have a straight line and you move it up and down, we could only get to 4.29 as the minimum loss after 100 epoch. So basically, more the epoch, the lower the loss in most of the cases. I'm not saying that it happens all the time, but it happens most of the cases. It happens in most of the cases. So this is also, but in the neural networks have a better tendency of predicting or fitting uh, the requirements of our prediction results or stuff. So this works well. So if we plot it, we can see that the loss is, I mean, the loss was 4 as we expected it. In the first step, the loss was about 4. And so the model is pretty good at this place, and it went down at a very high speed. So if we print the parameters, at first we have the type of parameters that generated in so many tensor. So this is what it gave us, okay, as a prediction. So if we match it, we will have, so we have 2 at this place, and what it gave us was 1.9980 and negative of 3.4012. At this place, we have negative of 3.4, and this is 1.2 and 4.2. Okay, so this is 1.2 and this is 4.2. So the model is very good. The neural network architecture, like, is the top class as of now, because it nearly predicted the weights and biases for the model which we gave it. And so at this place, it can predict a linear function very accurately, like exactly. So moving on, what we did is, right now we did plot it as x and y, and after every epoch, I will show you that the prediction and the estimated thing meets at one point. So basically, we have three real and three estimated. Why is that? Because we had x1, x2, x3, y1, y2, y3. So if we run this code, what I will get is, at the first, things were really scattered, but the estimation and real part, they started to come closer to each other after each epoch. And as loss is decreasing, the model can predict is very good. So as you can see that the model, yeah, is predicting stuffs at a very great pace, and we are getting what we wanted to. That as you can see here, that this parameter which it generated is nearly equal to the one which we fed the model. We did not we did not make the model read this stuff. The, like, what do you call that? The constants multiplying the independent variable, but the model predicted it after 10 epoch and running it on 10,000 values again and again and again. So this is how it works. After each loss, I mean, after each epoch, after each updation, the model predicted the value in a really great manner. So above, I was telling you how to use linear regression as a classification. So that happens is, let's say we have to classify a house as uh, cheap, medium, or expensive. So we can use linear regression and tell that predict the price of houses. Once we have the predicted housing price, we can define a function, let's say name, which takes a parameter of a, and it goes like, if a is less than $10,000, then print cheap 10,000, 100,000, that is around 80 lakhs. Else if a is greater than 100,000 and a is less than 1 million. I'm not writing it in a way that it runs, so just bear with me. It is, let's say, expensive, and if nothing, then print it as expensive. This will be medium. So this is how you can make a regression model work as a classification model, but this is not a good way to do it, because it may happen that there are many different factors to play. So you can also just let's say you can say the prices is equal to list and prices dot append price. So what is that? What it does is it adds all the price, uh, and then we do it as prices dot sort. So at this place, it sorts the prices of the houses, and we can say like sort prices. Then we can say like sort prices. So 10% of that, like first 30% of that is cheap, and from 30% to let's say 90% is where is the and symbol, is medium, and from 90% to 100% we have expensive. Then we can just write here sort prices, and this will work. So this is a way how you can use the linear regression model as a classification model. So this was all about your linear regression. I'll share this code base, and you can just go through it on your own, run the code, do some changes in the learning rate, and see how it works. So this was all, and I guess your what you call that, your induction into the team will be happening soon, and I wish you luck for that. And why am I talking like an old man? Anyways, thanks for the session, viewing the session, or anything like that.